Okay, so today we're going over a lot of stuff to do with the energy part of global systems and energy. Okay, and it is unfortunately going to be one of those really like empty vessel kind of days where I talk and fill the vessel. Okay, and I'm sorry about that. Just some days are going to be like that. Okay, so some important things that we want to get out of today. Okay, the theme here is things that come in threes. We are going to talk about the 3 types of energy transfer. We are going to talk about the 3 parts of the Earth and how they interact and how those 3 methods of heat transfer work in those 3 different parts of the Earth. Okay, so we're looking at the Earth as a big system, global systems, but we're also looking at the ways that energy moves from place to place. So this is going to relate back to the thermodynamic stuff from last unit. Okay, there's an element of that, but we're going to talk about some things that will hopefully be familiar from like junior high science. Okay, methods of heat transfer are conduction, convection, and radiations, like grade 8 science. Okay, where you would have taken that. Things like that. So we're going to talk about how those work. In terms of how are you going to be assessed on this lesson? That might be something you want to write down, by the way. Okay, how are you going to be assessed on this lesson? This lesson is like biology. It's application. Okay, I'm going to give you a situation, and you're going to have to tell me how is heat transferred in that situation, or how could you prevent heat from being transferred in that situation. Okay, so things like that. Be looking for and listening for, writing down examples of applications that I go over in this lesson, because that'll be very similar to the way it'll be asked on your open book Unit 4 assignment thing, okay, on the 21st. So it's really important to have the examples and the applications in your notes so that you can refer back to them for that day. Okay? Okay, so we got to understand and identify the 3 parts of the Earth, understand how energy on Earth is absorbed, used, and reflected. Sorry, that was the other thing of 3s. Okay? When light hits the Earth, there are 3 fates for that light: absorbed, converted, reflected. Okay, so there's lots of 3s here. Lots and lots of things coming in 3s today. Okay, and understand how energy and the Earth interact to produce the conditions necessary to support life. That's kind of application part there. Okay, first part of the Earth. Okay, and it's the one that energy coming to us from the sun interacts with first. Okay, and that would be the atmosphere. Okay. The atmosphere is the part of the Earth that is most responsible for transferring energy from place to place. Okay, it does play a role in absorption, reflection, okay, things like that. But its main job is to help transfer energy from place to place. Okay, where on Earth gets the most solar radiation? The equator. Okay, so if the equator gets more solar radiation than anywhere else, and the second law of thermodynamics says that energy has to go from hot to cold, okay, something has to help that energy move from the equator to the poles. That something is the atmosphere. Okay? Because the atmosphere is made of gases, it's very fluid. It can move very easily. Okay? What do we call moving air? We get lots of it here. Wind. Yeah. Okay? Wind is evidence that energy is being transferred from place to place. Okay? It's just like the heat engine. Okay? When energy has to go from one place to another, matter inevitably goes with it. That's what, changes in pressure can cause wind, but same with changes in energy. Okay? Things are naturally going to move from hot to cold, and we're going to feel that. It's called convection. It's one of the 3 methods of heat transfer. Okay? It's what happens in the atmosphere. Now, there are layers to the atmosphere. I am never going to ask for the names of these layers. They are completely unimportant. Okay? What I am going to talk about is how the energy that comes from the sun interacts with the atmosphere, and I'll use those names, but I will never ask for those names. Okay? I'll never have a question that asks, what's the upper layer of the atmosphere? A exosphere. No, I won't do that. Okay? So, when light first encounters the Earth, okay, it first actually hits our magnetic field. Okay, generated by the fact we have a solid iron core, okay, it spins and creates a magnetic field. The Earth is one big giant magnet. Okay, that magnetic field is what causes us to see northern lights. Okay, we've had some pretty good ones of those this year. Okay, what's happening there is we're seeing evidence of all the high energy particles that the sun throws our way encountering the magnetic field of the Earth. When they hit that, they slow down. When they slow down, they lose energy. Okay, and they lose it in the form of light. We can actually see the curtains, okay, of light falling down to the Earth as evidence that these particles have been slowed down. And it's actually kind of like shields in a science fiction kind of show or movie. Okay, they always have these imaginary energy shields that protect them. Okay, well, ours isn't imaginary. Our magnetic field is a big shield, okay, that deflects and slows all the really lethal stuff that the sun throws our way. Okay, we don't want that stuff to get to the surface. It's energy, but we don't want it, right? And gamma rays are not going to make you into the Incredible Hulk. Okay, they're going to fry you like an egg. All right, there's a lot of misinformation out there. Okay. All right, so the exosphere and the thermosphere is kind of where all of that happens. The mesosphere just kind of in the middle. Okay, stratosphere and troposphere are kind of the ones that are most important for us. Okay, that's where the air is thickest and where most of the weather occurs. Okay? There are only a few places on Earth that you can stand where you would actually be in the stratosphere. Okay? And those would be like the highest peaks in the world, so like Everest and K2 and places like that. Okay? What do they call the top of those mountains? You get to the top, you're in the
summit.
Okay, yeah, they do call it the summit, sorry. The area near the summit. It has a very dark name. It's called the death zone. Okay? Once you get above a certain altitude and you're essentially in the stratosphere, your body is slowly dying. Okay? It simply cannot maintain itself at those altitudes because there's not a lot of pressure. It's also very cold, okay? But there's not a lot of atmospheric pressure. There's less gas above you pushing on your body. Okay? Water will boil at about 65 degrees Celsius. Okay? You see people in tents at Camp 4 on Everest and they're eating boiling soup. Okay? They can eat the boiling soup because it's only 65 degrees Celsius. Okay? Water boils a lot earlier when there's less pressure keeping it as a liquid. Now, that's also a problem for you because you can get dehydrated a lot faster. You exhale, more water vapor comes out. Okay? And what can actually happen is fluid will start to build up in your lungs. Normally, we call that pneumonia. Okay? But if that happens at high altitude, it can kill you. Okay, so it's a big deal to be way up there. Your body is not, like naturally adapted to that kind of condition. You can only survive up there for maximum a few days, and then you have to come down. Now, in the troposphere, that's where we live. Okay, that's where all living organisms are going to be. Okay, all of the weight of the atmosphere is pushing down, so we've got lots of atmospheric pressure. Okay, all the good gases are down here, nitrogen, oxygen, okay, things like that. Okay, everybody good with that? All right, so what we're concerned with is the energy that makes its way to here. Okay, that means that it hasn't been scattered, okay, by the atmosphere. It hasn't been reflected by the white tops of the clouds. It has made its way down to the surface. Okay, everybody okay with that? Okay, let me ask you this. Why is the sky blue?
The reflection of the ocean.
Okay, I know somewhere somebody is teaching that. Unfortunately, they're wrong. What color is water? It's clear. So the ocean is blue because it actually reflects the sky. The sky is blue because the gases in our atmosphere scatter blue light. Okay, so when light comes in from the sun and strikes the gases that make up our atmosphere, blue light gets reflected off of the particles all different directions. That's what makes the sky blue. That's why the sky can be different colors in pollution situations. Like when we had all those forest fires years ago, what color was the sky? It was like orange, exactly. Okay, you get all that soot and particulate and smoke, and now suddenly longer wavelengths like orange are getting scattered instead, and it makes the sky look a different color. It's also why at sunset the sky is orange. As the sun gets closer to the horizon, it now has to travel through all the pollutants and heavier gases and particulates that are close to the ground. So it looks orange instead of blue. Okay, so just so you know, it's not that you guys were wrong at all, because I know somebody out there, I gotta find out who is teaching that the sky is blue because it reflects the ocean. But the ocean is clear, okay? It looks blue because it reflects the sky. The sky is blue because it scatters blue light. Okay, that means then that blue light doesn't really get to the ground very well, does it? Okay, a lot of it gets scattered away. If it's a cloudy day, is it generally cooler? Okay, because what's happening to it, a lot of the light? Does it get through the clouds? So some of it is going to be reflected by the clouds, and some of it's going to be absorbed by the clouds, and that's what can start to help creating those thunderstorm cycles and things like that. Okay? Whatever light gets to the ground, if we want to have a change in temperature, it has to be absorbed. Okay? The atmosphere can absorb light and get hotter. The ground can absorb light and get hotter. The ocean can absorb light and get hotter. Anytime there's absorption, temperature goes up. Okay? What about in reflection? Will temperature go up if the light just bounces off? No. If it reflects, nothing got absorbed. It simply bounced off. Okay? No energy would be transmitted. Okay, everybody okay with that? Okay, so this is kind of what happens in the atmosphere, this diagram on the left. Okay, so we got solar radiation coming in. Okay, a lot of it gets back scattered by the air. Okay, that's what makes the sky blue. Okay, some of it gets reflected by clouds because clouds are white. Okay, white reflects more light than other colors. Okay, in fact, white reflects all colors. What does black do? Absorbs all colors. Okay, that's why if you've got two cars side by side on a hot day in the parking lot, one white, one black, which one's hotter to the touch? Black's always hotter to the touch because black absorbs light more than white does. Okay, white reflects it away. So the tops of clouds on a cloudy day are reflecting away a lot of the sun's incident energy, and that's why it's generally cooler. Okay, so we could have some of that energy getting down to the earth. If it gets down to the earth, then it gets absorbed or reflected. Depends what the earth is covered in. Right now, what's happening to most of the energy that strikes the earth here? It's getting reflected because it's wintertime and there's snow out there. Okay, this is something you can use all the time. Okay, it's a property called albedo. In fact, this is a really super important word that you need to know. Okay, the reflectivity of the Earth's surface is called albedo. Okay, if something has a high albedo, it's very light in color and would be highly reflective. If it has a low albedo, okay, then it's darker in color and is going to be more absorptive. Okay, this is something we use in Canada all the time to our advantage to help keep the streets free of ice. Okay, if it snows, the plows go out, they try and clear as much of it as they can, but some of it gets packed. What do we throw on top of that? Rocks, sand, okay, and usually some salt as well. Okay, is sand dark in color? Okay, so if I throw sand on a bunch of ice, will that lower its albedo and make it absorb more energy? It will. And if it absorbs more energy, will its temperature go up more? Okay, so that means it's there to help melt the ice. It also has the added benefit of increasing traction. Okay, putting a bunch of little rocks on top of something really slippery also helps with traction, but It's mostly there to help melt the ice. That's also why we often add salt to it. Okay? Adding salt lowers the melting point of the ice. Okay? It makes it melt faster. Okay? Everyone kind of follow me there? Okay? So there's kind of multiple applications for that. Okay? Like I just used this the other day in my backyard. Okay? I knew it was going to get nice and I wanted to be able to take down some of my Christmas decorations. Okay? But they were, some of them, buried in snow. All right, so what I did is I just cleared around them a little bit, knowing a Chinook was coming, okay, so that I could see the darker colored ground, or grass, or whatever, okay, that was around them, so that when the sun came out, I knew it would thaw the ground enough I'd be able to pull the stakes out. Worked perfectly. Okay, simple application of lowering the albedo of something to make it absorb more energy. Okay, you want snow to melt faster, throw some dirt on it. Okay, it'll make it darker, it'll melt faster. Okay, making some sense? Okay. All right, so this would be kind of comparison of the energy input for seasons. Okay, so if we're talking about a place like in our area, in the summertime, okay, a lot of the energy is going to be absorbed because there's no snow. Okay, you're either going to have bare ground that's usually dark in color, or it's going to be covered by plants. Okay, also dark in color. Okay, they can also not just absorb, but they can convert that solar energy. How do they convert it? Photosynthesis, yeah. Okay, so the three fates for light, okay, these are important. The three fates for light, okay, we'll just write them down here. Okay, three fates of light. One could be absorbed. Okay, that usually means low albedo. Okay, and energy increases. Actually, energy slash temperature, let's say. Okay, the second fate of light, it could be reflected. Okay, and the third fate of light, conversion. Okay, sometimes it's called use. Okay, and that is photosynthesis. Okay, those are the three fates of light when they strike the earth. Some of it will be absorbed. If it's hitting something dark enough in color, okay, it will be absorbed. Okay? If it's hitting something lighter in color, then it will be reflected. And if it hits plants, it will be converted. Okay, so if we're looking at these side-by-side comparisons then, okay, in the summertime, generally we're going to see darker colors and more plants that are active. Okay, so about 70% of the light coming in, the incident light, okay, is going to be absorbed or converted. Okay, 70% of it. All right, about 10% will get reflected off of water bodies because they're a little bit more reflective when there's, at the right angle. They've got a lot of glare, that's reflection. Okay, and about 20%, okay, would be reflected off of light-colored surfaces. Maybe you've got some light-colored rocks, okay, or something like that, okay, and it would be reflected off of that. But 70-30 is the ratio between absorption, conversion, and reflection, because the albedo is generally lower in the summer. All right, now, go to winter. You got this whole area now covered in white snow. 85 to 90% of the incident light is reflected away. Okay? That makes it really hard to get anything going, okay? Including the water cycle. Okay? You can't get the water cycle going if all of the energy is just getting reflected off of the snow. You can't melt the snow, you can't evaporate the water, okay? And everything kind of stalls. That's why deeper into winter, unless we have a front move in that brings a lot of moisture, it typically gets drier. Okay? There's just simply not enough energy to keep that water cycle going. Okay? Everyone okay with that? Right? You might have the odd spot where some stuff is being absorbed, trees that are sticking out of the snow, okay? Maybe a rock, okay, a dark colored rock that's sticking out of the snow. Okay? You'll see that now that if you start looking for it, you'll see that usually things that stick out of the snow around them melts faster. Okay? They're simply darker in color than snow is. Okay? They're going to absorb because they have a lower albedo, okay? And things are going to heat up quicker around them. Okay, so we got to know albedo. We got to know the three fates of light. All right, here's something you want to write down. Here's exactly how I'm going to ask about this. I'm going to take a screenshot of a Google Earth picture. Okay, I'm just going to pick a place on Earth and take a little snippet of it from Google Earth. Okay, and I'm going to put that on the test. You're going to have to look at that. It'll be in color. Okay, and tell me what's going on here in terms of the three fates of light. Okay, so if you look at it, and I have picked like the Columbia ice fields, okay, and it's nothing but snow and ice, okay, is it going to have a very high albedo? High albedo means very reflective, so it'll have a very high albedo, okay? That means most of the energy gets reflected, okay? Very little of it will be absorbed except by maybe any rocks that are sticking out, okay? And any plants, generally not at that altitude, so probably very little to no conversion of the light happening. You would just have to tell me, here's how much of those three fates are going on in that situation. Okay, if I showed you a picture of the Amazon rainforest, obviously the question would be basically reversed. Okay, most of the energy will be absorbed or converted due to dark colors and the presence of lots of green things carrying out photosynthesis. Sort of make sense? Okay. So atmosphere has a lot to do with climate, okay, because again, its main role is to transfer energy from place to place by convection, okay. It also plays a role in helping to trap heat, okay, through the greenhouse effect, which really gets a bad rap that it doesn't really deserve, okay. If Earth had no greenhouse effect, it would be a ball of ice. Okay? In fact, Earth has had a period of time in its past where it had so little CO2 in the atmosphere that it actually caused a global ice age, okay, like hundreds of millions of years ago, and that period of time is known as snowball Earth. Okay? So having some CO2 in the atmosphere is important. Do we want the amount to accelerate wildly? Absolutely not. Okay? But having some CO2 to provide a greenhouse effect that traps gas is actually, that traps heat, okay, is actually important for maintaining a temperature that is conducive to life. Okay? So the greenhouse effect actually plays an important role in keeping the conditions on Earth habitable by trapping some of that radiation that would otherwise reflect off. Okay? So energy can come in, it can be absorbed. Some of it gets reflected off the surface, but some of it will hit the greenhouse layer, okay? And it will reflect back. That gives it a second chance to be absorbed. That's the warming effect of the greenhouse effect. Okay? Obviously, we don't want it to get out of control. Okay? If it does, we'll end up like Venus. Okay? Venus has a runaway greenhouse effect. Its atmosphere is almost entirely carbon dioxide. okay? Thick layer of clouds, okay, sulfuric acid, and temperatures at the surface that are hotter than your oven on the self-cleaning cycle. Okay, so certainly not the situation we would like to have. Okay, certainly not habitable. Okay, but it's a very different place, right? Our greenhouse effect is never going to get that crazy. All right. All right, questions on that? So that's just, again, that absorption, reflection. If it gets reflected, it may get a second chance to be absorbed due to the greenhouse effect. Okay, now, hydrosphere. So that's the atmosphere. Atmosphere transfers energy, okay? And we've talked about albedo and the three fates of light. Okay, now we got to talk about all the water on Earth. What role does it play? Okay, well, the atmosphere deals with what we call sensible heat. That's the heat we can feel, okay, whether it's warm outside or cold outside. The hydrosphere deals more with something called latent heat. Okay? Sensible heat is kinetic thermal energy. It measures how fast particles are moving. Latent heat is potential energy. It's due to the state that the water is in. Okay? Which state would water have the most latent heat in? Steam, water, or ice? Which one would have the most energy? Which one do you have to add energy to make?
Steam.
Steam, yeah, okay? Because as you change state, remember like what particles look like in a solid, right? They're tightly packed and all they can do is move around a little bit, okay? When you melt a solid, okay, the melting part actually is moving the particles further apart, okay? Now they can move past each other. That's why liquids can be poured and flow from one thing to another, okay? If you warm up a liquid enough, the particles get even further apart and become a gas. The distance between the particles is latent heat. The further apart they get, the more latent heat or potential thermal energy they have. Okay? How many have been told this? Be really careful, steam will burn you worse than water. Okay? I mean, it's important to know, right? And it's absolutely true. Even if the water and the steam are both exactly 100 degrees Celsius. The steam will burn you worse, even though they're the same sensible heat. Their particles have the same kinetic energy. The difference with steam is the particles are this far apart. If that steam condenses back into a liquid, what happens to all the energy that was keeping the particles apart? It gets released. Okay? So what burns you badly with steam is actually all the potential thermal energy that it contains. So if you get steam that hits your arm, that steam condenses back into liquid water and releases all the potential energy that it had, and that can cause a deep tissue burn. And then you've got the problem of you still have water that's 100 degrees on your skin, okay, to, put salt in the wound, okay, on something like that. That's why steam is so much more dangerous, okay? It has that much more energy, okay? To give you an idea, 1 gram of steam at 100 degrees Celsius has 2,260 joules of more energy than liquid water at 100 degrees. 1 gram, that's 1 milliliter of water, has that much more energy in it. Okay, that's why steam can burn you worse. Okay, so the hydrosphere operates on the energy from latent heat. At the equator, there's more energy. Will water evaporate off the ocean? Okay, and that water vapor will move up into the air. Can it be pushed to other parts of the world by wind? Does it take with it all of that energy? Yeah, and when it arrives in another place, and then maybe it condenses, it releases all of the energy that it absorbed at the equator to that other place. Okay, it transfers energy by latent heat. Okay, that's the main role of the hydrosphere, is to use the water cycle, okay, evaporation, condensation, precipitation, all of that to transfer energy from one place to another. Okay, so I know you've been beaten over the head with the water cycle, like probably 6 out of your 10 years of schooling. One more time, okay, because we got to talk about it now in terms of energy. Okay, there's not just thermal energy carried through the water cycle, there's other forms as well. Okay, so for evaporation to occur, does energy have to be absorbed? It does, right? The energy has to increase in order for water to become steam. Okay, so when this absorbs this water and moves up into the atmosphere, okay, it can be blown to another place over here. When it condenses, it releases the latent heat. That's huge, okay? 2,260 joules for every gram of water that condenses gets released into that new area, okay? You think about a thunderstorm, how many thousands of liters of water, probably millions of liters of water, are in a thunderstorm, okay? When we get hail and all that kind of stuff, think about how much water is in there. That's a lot of energy, okay, that's being released. But it's not just that. That water condenses, it releases the thermal energy. But when that falls, does it get into rivers? Okay, so it's here on the top of the mountain. Does it also have mechanical energy? Right? It's at a high altitude. If it's a liquid, it's going to flow through rivers and streams. Okay? If we put a dam on that, can we use it to generate electricity? Where did that energy come from in the first place? Came from the sun. Okay? Anything that we use as energy on Earth, be it hydro, okay, or burning fossil fuels, all of that was solar energy at one time. Okay? It's just in here, okay, there's so much energy being absorbed and transferred through the water cycle, okay, that we can use it as thermal energy, kinetic energy, potential energy, all of it. Okay? The water cycle represents a huge amount of water and energy. Okay? Everybody all right with that? So, do you need to know the parts of the water cycle? Yes. Here's why. Okay? You need to know that for evaporation to occur, energy needs to be absorbed. Okay? So this is the energy in part of the water cycle. Okay? Over here, when we have condensation, precipitation, runoff, that's the energy coming back out. Okay? When it condenses and precipitates, that is thermal latent heat coming out. When it's running off in rivers and streams, that's mechanical energy coming out. Okay? But all of that energy just continues to cycle as long as the sun is able to drive that cycle. Okay? Now, can the sun drive that cycle in Antarctica? What's Antarctica covered in? Yeah, snow and ice. Several kilometers thick in some places. Okay? What's the driest continent? It's Antarctica. Antarctica gets less precipitation than any other continent on Earth because the water cycle can't get going. Okay? It can't absorb any energy because it's all white ice. Okay? And then, as a result, you just don't get any evaporation, you don't get any precipitation, nothing. Okay? The only reason Antarctica is covered in a kilometer thick sheet of ice is because it's been down at the bottom of the world, okay, for, well, a couple of million years at least, okay? And even if you only get this much snow a year over a couple of million years, it adds up. Okay? That sort of makes sense? Okay? That all goes back. There's another application kind of question, right? It brings in albedo, it brings in the water cycle, it brings in energy. Okay, now, I forgot to take that slide off. Okay, so what's on that slide in terms of text, not important, okay? But if we're looking at like a glacier, for example, okay, does that glacier still hold some energy from the water cycle from ages ago? It does, okay? Not any thermal energy, because it's ice, okay? But it still holds the mechanical energy. We find glaciers at the top of mountains, and as they melt, okay, that potential energy turns into kinetic as the water flows through the rivers, okay? So even glaciers still represent some storage of the energy from the sun from ages past. All right, third part of the Earth. The lithosphere, okay? Litho means stone, so this is the rocky part of the Earth. Okay, so the role of the lithosphere is not at all to transfer energy, okay? Because the lithosphere can't move, right? It's solid. The particles are stuck. They can't move past each other, okay? And so very little energy is transferred through the rocky part of the Earth. The role of the rocky part of the Earth is determining the albedo, okay? Is it dark, is it light, okay? And providing soil for plants, because plants have a big role to play. They're part of the three fates of light. Okay? If there's good soil, then there could be good plants there, lots of plants carrying out photosynthesis, absorbing and converting the light. Okay? So probably the most important role, okay, of the lithosphere, okay, has to do with providing soil for the plants. I need that one anyway. Okay, so soil is the topmost layer of the Earth's surface. Obviously, that's where plants can grow, okay, and it is its own ecosystem made of biotic and abiotic stuff. We talked about that back in the biology unit, okay? Now, how many people in here have ever dug a hole? Okay, when you dig a hole, okay, provided you dig it, let's say, more than a couple of feet deep, what do you notice? Does the dirt change as you dig? What do you usually hit once you get through the topsoil? Usually hit clay, okay? Rocks, clay, okay, when you get down below, right? That's because soil is layered, okay? The top layer, that's the top soil. That's the part that plants want to be in. That's where all the nutrients and organic material and decaying plants and animals are, okay, that provide what they need, okay? But below that, okay, is usually a layer of clay, and then interspersed below that is usually the bedrock, okay, where you start to see the rocks. Here in Okotoks, you don't have to dig very far to get down to the bedrock, all right? Because our soil structure here has really nice topsoil, generally, okay? But then fairly close to that underneath, there's like a thin layer of clay, and then you get into the rocks, okay? There's a big outcropping of sandstone here in our town, and so that we can get to that pretty easily. And if you've ever had to dig holes of any depth here, you hit rocks almost right away. Okay? All right, so the layers of the soil. Don't worry about the O horizon. I'm going to take that off. Okay, we're going to have A, B, and C horizons. Okay, so A, B, and C horizons. A is the topsoil, B is the subsoil, clay, okay, and C is the what we call parent material or bedrock. Okay, is soil the same everywhere you go? Dirt's different everywhere you go. Why? Like around here, our dirt is actually very sandy. Okay, like it's very gritty. Even the topsoil, if you put it between your fingers, you can feel the grit. Okay, whereas if you go up to like even just north of Red Deer, if you take dirt in your fingers and do this with it, it feels more like flour. It feels very fine, almost slippery. Okay, it's also much blacker. Right? Our soil here tends to be more of a light brown color. Okay, whereas if you go further north, it gets much darker. Okay, it gets darker because it's made of different stuff. Okay, here, our bedrock, the parent material of our soil, the rocks that weather and make our dirt, are mostly sandstone. So our dirt is very sandy. Okay, if you go further north where there's more limestone, okay, then the dirt is going to be darker and finer because when limestone breaks down, it makes much finer, smaller particles. Okay, so it feels more slippery between your fingers. Okay, if you go to PEI, their dirt is red. Okay, and they like have tourist shirts that you can buy that they stain called the dirt shirt. Okay, but their dirt is very red because their parent material there is much different than it is here. Okay, if you go into the Canadian Shield, same thing. You're going to have different kinds of dirt because you got different kinds of rocks that are breaking down to make it. Okay, so the parent material determines the soil structure. That said, no matter where you go, the middle layer is always going to be clay. How does it get there? Like if you had a sandbox as a kid, okay, if you dug down through the sand, there was always clay underneath, okay? Like I know, I built the sandbox for my kids. I know I didn't put clay in the bottom of the sandbox, yet after a few years, there was clay in the bottom of the sandbox, and it wasn't because they put it there. That layer naturally forms, always. Okay? The reason for that is clay as a particle is incredibly fine, very, very small. It's actually dust that has fallen on the ground and then been washed down under the topsoil. Okay? Because topsoil particles, okay, are large and kind of irregular in shape. Clay particles are very small. So when that dust settles on top and then it rains, those little particles will wash down between the spaces of the larger particles and they collect underneath. Okay? The nice thing about clay, it retains moisture. Okay? So it helps the soil to retain moisture by having its ability to hold it underneath. Okay? All right, so just know the horizons A, B, and C. Okay? Good on that. All right, so the A horizon, topsoil, mixture of decomposed rock, living organisms, decaying organic matter. Okay, this is a pretty typical soil horizon for our area. Okay, darker topsoil, subsoil made of clay, sandstone bedrock underneath. Okay, around here, because we live in a grassland ecosystem, our topsoil is generally pretty thick because every year the grass dies and then grows from the roots again. So all the blades of grass from the previous year build up a layer that we call thatch. Okay? And that thatch eventually breaks down and forms more soil. Okay? You also see this in central Canada, where every year the trees lose their leaves. Okay? So you get this layer of leaf litter every single year that just decomposes and makes the soil thicker and thicker. Okay? Everybody all right with that? Okay, B horizon, very little organic material. Okay, rock is less decomposed, and there's a lot of clay in the B horizon. Okay, and then the C horizon is the parent material, okay, because it's where the soil comes from, so that's why we call it parent material. Okay, you can also call it bedrock. Okay, here's a soil horizon from our local area here. Okay, so you can see that the A horizon, okay, is probably, well, use a color you can see. Okay, it's probably about there. Okay, the B horizon would be kind of along this line. You're still going to get chunks of rock everywhere. Okay, but below that is mainly rock. Okay, so A, B, and C. All right, going to give you guys about let's say a 4-minute break here. I'm going to stop talking for about 4 minutes, okay, and then we'll pick up here in just a second. Okay, so if we're looking at the energy coming in and the energy going out, okay, for Earth, obviously it's the energy in that we can do work with, okay, that can, power photosynthesis and then be used for other things. Okay, if we're looking at the 100% of the light coming in, okay, about 6% of it gets backscattered. That's the blue light, makes the sky blue. Okay, about another 20% of it are reflected by the tops of clouds because obviously they're white. Okay, if we're in a low albedo situation, only about 4% would be reflected by water and land surfaces, and that would leave about 51%, okay, being absorbed by the Earth, 3% being absorbed by clouds, and 16% being absorbed by water vapor, dust, and CO2. That's that greenhouse effect part of it that we were talking about there. Okay, we're talking about the outgoing radiation. A lot of that is the stuff that gets reflected. Okay, it's going back out. Okay, as well as sensible heat, the stuff that we can feel. Okay, latent heat, that's the whole water cycle part there that we know actually ends up coming back. About 23% there. I'm not going to ask you at all about those numbers. Just have an idea of, okay, well, a lot of it gets reflected in these situations. It's mostly about albedo. Okay, that's what we're most concerned about there. I'm never going to ask you for these numbers. Okay, I'm going to skip that one. Okay, all right, transfers. So here's where we need to know another set of 3 things. Okay, the 3 things we need to talk about are conduction. Okay, convection, and radiation. These are the 3 methods by which energy is transferred. Thermal energy, that is, okay, is transferred. Okay, conduction is heat transfer in solids. Okay, so conduction only happens in solids. Okay, and it is caused by the direct collision of particles. Okay, this is why you don't, like, if you're making soup and you're, simmering or boiling water for a long time, why you don't leave a metal spoon in there. Okay, metals typically conduct heat very, very well, and the handle of that spoon will be really hot in pretty short order. Okay, but something like wood that's more porous doesn't conduct heat very well. You can safely leave that in the soup, and the end of it's never going to get hot. Okay, so conduction happens because particles are running into each other. Okay, so imagine like you're playing pool and you're about to break, right? You got the whole set of balls there that are in the triangle, right? You shoot the cue ball at it, even the ones that you don't hit with the cue ball still move. Okay, that's what it looks like at the atomic level for particles. Okay, one particle gets moving, it hits a neighboring particle, it causes it to move. Okay, every time a particle starts to move a little bit faster, that heat travels up or along that solid material. Okay, it's kind of like a mosh pit. Okay, you got everybody jumping around and they're banging into each other. Okay, and all that motion eventually can transfer out a long way. Okay, that sort of makes sense what conduction is. Okay, but conduction only happens in solids. So if you've got 2 solids in contact with each other, conduction can transfer heat between them. Okay, convection. Convection only happens in fluids. So that's liquids and gases. Okay, convection is currents that move thermal energy. So hot air rises, cool air descends, that's convection. Okay, so anytime a fluid can flow or move, it can transfer heat by convection. Okay? That is generally how most of our houses are heated. Okay? Most of us would have a forced air furnace, okay, in our house. Okay? So there's a big gas heating element in there. Okay? It burns the natural gas and a fan blows that hot air up through your floor vents. Okay? Because hot air naturally rises, okay, it passes the coldest air that's near the ground, okay, and then it warms the room. All right? You also have, along the floorboards in your house in a few places, cold air return ducts. Okay? They're usually on the wall, where heating vents are usually on the floor. Okay? That's allowing the cold air to go back in and back down to the furnace, and it sets up a convection current in your house. All right? The last one is radiation. Okay? This room uses radiant heating. Okay? There's hot water pipes that run along the back wall and along the outside wall. Okay? If they want to heat, if they want to turn on the heat in this room, okay, then they just run hot water through those pipes. Okay? And the heat just radiates off of those pipes. Okay? You can feel heat being transferred by radiation, okay, by feeling heat coming off of something. So if you go up to a campfire, right, you can feel the heat coming off. That's radiation. Okay? Radiation is not always the thing that turns you green, okay, and makes you glow, right? It can be, okay, it is a transfer of energy, but we're talking about thermal energy here. Radiation by thermal energy is waves of heat. Okay? Radiation is how energy gets here from the sun, because conduction and convection both require matter. Energy has to flow through the vacuum of space to get here, so it gets here by radiation from the sun. Okay. There will be an application question about these three methods of heat transfer. In fact, there'll be a few. Okay, so you need to know that conduction is particle collisions transferring heat in solids. Convection is currents, hot air rising, cool air descending. That comes up all through the unit. Okay, and then radiation is waves of thermal energy coming off of something. Now, being that it's winter here, okay, we obviously have to keep our houses warm. We don't just want to run a furnace constantly non-stop and just have energy bleed out into the outside air all the time. Okay, so how do we prevent energy from escaping our homes? Insulation. Okay, so that's probably the biggest one. Okay, so if we're kind of diagramming this, guys, if I just have a wall, okay, with no insulation, okay, there would be air inside that wall, right, between the pieces of drywall, right? So inside is hot, outside is cold. So what's going to happen is the air closest to the inside wall will get hot, and it will rise. Cold air from the outside wall will move in to replace it. Okay? And then this cycle will just keep happening. Is that a convection current? Hot air rises, cool air descends. If you don't have insulation in your wall, you are just absolutely bleeding energy right through the walls, okay? Because you're allowing air to circulate inside the wall. So what we do is we fill our walls with insulation. What's insulation usually made out of? Usually two materials. What would they be?
Fiberglass.
Fiberglass, okay, that's the pink stuff. Sometimes it's yellow, okay? And what else? Starts with S. Styrofoam, okay? Or some sort of porous foam, okay? So let's look at what this would look like if we're talking about insulation, the fiberglass variety, okay? So if I have fiberglass, if you've ever seen this stuff, it's nasty actually, okay? It is made up of millions of tiny little glass fibers. You definitely don't want to handle it with your bare hands. You'll get little pieces of the fiberglass in your skin. They'll break off. They hurt. They're always there. They're hard to get out because they're hard to see. Okay? You also don't want to inhale it. You can inhale small pieces of fiberglass. You usually wear a mask when you're installing it. Okay? But what it really looks like is just a tangled mess of glass fibers. Now, one of the reasons we use fiberglass is because it doesn't conduct heat very well. Okay? As a solid, glass is a very poor conductor of heat. Okay? But also, now that my wall is filled with this, is there still air in there? There is, but now that air is trapped, and it's trapped between the fibers of the insulation. So can it move? Can't move, it's trapped in the insulation. So insulation prevents a convection current from happening inside your wall. Okay? And in that way, it does a very good job of it. Okay? It prevents the flow or the movement of a fluid, air, okay, from transferring heat out, or from inside to outside. So what parts of your house are going to be most prone to you losing heat? Not your walls, but you generally look through them. Your windows. Okay? Windows don't have insulation. Okay? Not only can radiation go straight through them because they're transparent, okay, but conduction can also happen very easily, okay, because you've got hot air right against one side and you've got cold air against the other side. Okay? So what do we generally do? Okay? We make our windows either double paned or triple paned. Okay? Modern windows are moving more towards 3 panes of glass. Okay, so if you have a triple pane window, you've got 3 panes of glass in that window. Okay? In here is either an inert gas or a vacuum. Okay? If there's a vacuum in here, that means there's nothing in there, right? Okay? Then if there's no air in there, can it circulate? Okay? A vacuum is actually a great insulator. Conduction can't occur through nothing. Convection's got nothing to move. Okay? Really about the only thing that could happen is radiation. Can't really stop that, it's going to go through. Okay? If we want to stop radiation, we draw the blinds or the curtains or whatever, okay? So that we're not allowing stuff to move out through the window. Okay? Making sense? It's a lot of the things you don't really think about that we do that have a purpose, okay, and a basis in methods of heat transfer. Okay? So here's another one. Okay? My coffee cup, okay? I find the Yetis aren't as good as the thermos ones, but okay, they all have a very similar design. Okay, there's an internal cylinder where obviously the coffee goes. Okay, so there'd be this part here, so the coffee goes in there. Okay, and then at the top, these two are connected, and then there's the outer part of the cup. Okay, and they are welded together up here. So right now, what's the hottest part of my cup? Down here or up here? Where's there contact between the inside layer and the outside layer? Right here. This is warm to the touch up here. There's not even any coffee up in that part of it, okay? But that's the hottest part because what's happening here? Conduction, convection, or radiation? 2 solids in contact with each other is? Conduction. Okay? And this is the flaw, the fatal flaw of all Yetis. Transparent plastic lid. Okay? Can heat radiate out the top of the lid? Yeah, and there's no insulation in there. There's maybe like a little gas layer or something in that plastic, but okay, there's not much to it. That's the fatal flaw of the Yeti is their top. Okay? If you have like a thermos, they generally have like a couple of layers of insulation in there, but for any cup, the biggest spot where energy is lost is where the 2 layers touch. Okay? That can actually happen in your house as well. Okay? If it's really cold outside, next time it's like really cold, like -30, okay? Run your hand along the wall. You'll become a stud finder. Okay? You'll be able to tell where the frame, the studs, the wooden studs of your house are because they'll feel colder. Right? Because they're actually in contact with the outside of the house and the inside of the house. There's no insulation where the board is. Okay? So you'll be able to feel the colder parts of the house there. Okay? Making sense? All right, so this is the kind of thing I would ask you, okay, as an application of this on the test. build something that would keep food and drinks cold on a hot day. Okay, so if I want to keep food and drinks cold, what color do I want to make it? White. I want it to reflect as much of the incoming radiation as possible. I want a light color. Okay, what else do I want to do? How do I prevent convection from happening? What do I need to fill it with? Should I have like styrofoam or something like that? Like if you ever look at styrofoam, it's actually a whole bunch of little air bubbles inside of that foam matrix. If you ever use the spray foam, it's the same thing. When you spray the foam, it expands and gases get caught in little bubbles inside the foam. And they prevent convection, they prevent conduction, because conduction can't happen through a gas. Okay, so they do a good job of that. That's usually what coolers are filled with, is some sort of spray foam. Okay, and do I want to make sure that it's sealed? Yeah, because if it's not sealed, convection is just going to happen, right? It's going to move in there. I don't want to leave it open for long periods of time. I want to open it up, grab what I want, and close it. That's why your parents get on you for staring into the fridge, wondering what you're going to eat. Okay? Like, know what you're going to eat, open the fridge and get it. Okay? Making sense? That's the kind of thing I'll ask you. Or here's a situation. Why is this going to work really well? And you can talk about things like albedo, conduction, convection, and radiation. Okay? You'll definitely get a question like that. I only saw a few people write that down, but I'm telling you, one of the questions is going to be on your test thing on the 21st. Okay? All right, and then what about preventing radiation? On my walls in my house, what would be best at keeping radiant energy in? Should I paint my walls light or dark? Which one's going to reflect the heat back? Light color, yeah. Generally want to have light colored walls, they'll reflect the heat back to me. In fact, lots of insulation now actually comes covered in foil. Okay, and the foil is reflective. In fact, let's talk about foil here for just a second. Okay, what I'm about to show you will keep you from being embarrassed at a barbecue. Okay? Okay, standard kitchen aluminum foil. Okay? Are the sides different? Why? Why are the sides different? One side's really shiny. I would argue it's reflective. The other side is dull, meaning it's probably absorptive. Okay, if you want to bake a potato on a barbecue, which side needs to face out? The dull side. You would be surprised how many people don't know that. I've gone to a lot of barbecues, okay? And I've seen people wrap the baked potato. In fact, I've seen them pre-wrapped at the grocery store the wrong way. Okay, I look at that potato, I'm like, that thing is never going to cook, because all you have done is made sure all the radiant energy from the barbecue is going to reflect off. Okay, instead, we wrap it with the dull side out. Energy gets absorbed, travels through the potato, and then hits the reflective side on the other side of the potato, and bounces back through the potato. Okay, travels, just bounces around in there. Okay, whole bunch of heat, cooks the potato really, really fast. Okay? How many people have an emergency kit in their car? If you don't, you should. Okay? They all have an emergency blanket. What's it made out of? It's just foil. It's a foil blanket. Okay? Put the shiny side in, you'd be surprised how hot you get. Okay? Just by being wrapped in foil and having the shiny side catch all of your radiant energy. Okay? It takes up way less space than like a cloth blanket. Okay? Now, a cloth blanket, does that keep you warm by preventing convection or preventing radiation? cloth blanket is interspersed fibers, like this. It prevents convection. This prevents radiation, reflects it back at you. Okay? If you really wanted to keep warm, you'd wrap yourself in this and then put the blanket over top. Then you're preventing everything. Okay? See, you're learning survival tricks all the time here. Okay? It's going to save your life one day. And save you embarrassment at a barbecue. Okay? Dull side goes out because that absorbs the energy, reflective side in. All right. Okay, now, so transfers within the atmosphere, radiation, certainly it's going to travel through, it's going to be absorbed, reflected, converted, okay? We're also talking about, for the hydrosphere, okay, for the hydrosphere, we're mostly talking about a little bit of convection, ocean currents are convection, okay? But mostly for the hydrosphere, we're talking about latent heat, okay? So the hydrosphere transfers energy through latent heat, okay? And we could even say like the water cycle. Okay, so you can just say hydrosphere, okay, transfers energy, latent heat, water cycle, okay, good with that. Okay, and then for the lithosphere, okay, the lithosphere, big part of the lithosphere is albedo. Okay, is the lithosphere light in color in that location or dark in color in that location? Okay, and of course, soil. Okay, because that is part of, okay, plants and conversion by photosynthesis. Okay, so if you didn't get these written down before when I wrote them down, okay, get them written down now. That's the 3 fates of solar energy, okay? If it's reflection, no energy change, that's determined by albedo, usually a high albedo, okay? Absorption, energy is gained, temperature increases, also affected by albedo, usually a low one, okay? And then you also have conversion by plants. Okay, so big things for today. The 3 sets of 3. Atmosphere, hydrosphere, lithosphere. Okay? Atmosphere's role, transfer thermal energy. Okay? Hydrosphere's role, transfer thermal energy through the water cycle, latent heat. Okay? Lithosphere. Okay? Lithosphere, job to absorb energy and provide soil for plants. Okay. Second set of 3, the 3 fates of light. Reflection, high albedo, no change in energy. Absorption, low albedo, increase in energy, increase in temperature. Conversion, Okay, absorption, conversion through photosynthesis to chemical energy or glucose. Okay, and then the three methods by which energy is transferred: conduction, convection, radiation. I would say probably 60% of your unit thing that we're doing on the 21st relates back to those three sets of three. Okay? They apply to a whole bunch of things that we're going to talk about in this unit, so they're always a good thing to mention in an answer. Okay? They can always be applied if we're talking about transfer of energy, okay, or things like that. Okay, questions on that stuff there, guys? I know it was a lot today. It's just one of those lessons where I've got to talk a lot. Okay. Tomorrow we're going to look at convection specifically. Convection is always going to be the really big one because tomorrow we're going to look at wind patterns. Okay, that's part of the components and factors of affecting climate. It's related to convection. It's related to energy. Okay, so it's going to tie back in there. So we'll talk about that, as well as we're going to talk about specific heat capacity tomorrow. That relates to why being near an ocean affects your temperature. Okay, there'll be a little bit of calculating with that, so please make sure you bring a calculator with you tomorrow, okay, for those questions. All right. Okay, guys, it's rapidly coming to a close here. Okay, I know that you're probably, a bit relieved that your thing on the 21st and the thing on the 22nd are open book. But remember, for that open book to be useful, it needs to be organized. Okay? And all through this unit, I'm going to mention, here's something you're going to want to be able to refer back to for a question. Here's a question I'm going to give you. Okay? Keep your notes organized so you know where everything is going to be. For this test, that'll be easy because it's a short unit. Okay? But when we're talking about that readiness check thing that used to be the mock, okay, that you can use to replace your lowest exam mark, you're talking about your notes for the entire year. Okay? Spend a little bit of time here over the next little while getting your notes organized so that you know where everything is. Okay? Realistically, on the 22nd, you won't have time to go back and forth and look everything up. Okay? There just won't be. So you still need to know it reasonably well or really know where it is so you can find it fast. Okay? The thing you want to have that you can find fast for chemistry and physics, example problems. Okay, know where they are, have them organized by type so you can find them fast. Okay, for biology, that's going to be diagrams. Okay, diagrams and really important things like tropisms and stuff like that. Know where those things are so you can find them fast. Okay, the key is to be really organized so you can maximize your chances on those. Okay? All right, so as I said, you have nothing else that you are going to hand in to me. Okay, I'm not taking anything else in from you other than the 21st and the 22nd. There's no more homework from me except to get organized. Okay, that's going to be the big thing. All right, we'll leave it there, guys.